The next speaker is Modibo Camara, Computationally Tractable Choice, the winner of the Best Paper with the Lead Student Author Award.
OK, hi everyone on Gather as well. So my name is Modibo Camara. I just graduated from Northwestern. I'm doing a postdoc at UChicago, and in a year I will start at Stanford GSB. So the title of this work is Computationally Tractable Choice. OK, so this work begins with two observations. The first observation is that people have only a limited amount of time in which to make decisions, whether that's a few seconds, a few months, or even a few years. Second, making good decisions can be time intensive, and this is something that we know from both computer science and from psychology. So this paper is asking, what are the implications of these two observations for behavior? Now, a natural place to start is to look at the available empirical evidence. And by and large, that evidence suggests that people respond to time constraints by using behavioral heuristics. These are simple rules that help us make complex decisions quickly. One example of a behavioral heuristic that will be especially important in this talk is called choice bracketing. So choice bracketing, roughly speaking, says that when a decision maker faces multiple different decisions, she will make each decision without considering the rest. And this is something that has found widespread empirical support both in the lab and outside the lab. So what I want to do is I want to start with an example of choice bracketing and then try to understand it from a computational perspective. OK, so I'm going to be talking about an American Economic Review paper from 2007, which studies bike messengers in Switzerland. And bike messengers are basically delivering small letters or small parcels from one part of the city to another. Now, this is an interesting setting from a labor economic standpoint because bike messengers have quite a bit of flexibility, both in terms of when they work and how intensely they work. So these bike messengers are going to sign up for daily shifts of 5 hours. And then within those shifts, they're going to complete some number of deliveries. And you can imagine by pedaling the bike faster or otherwise putting in more effort, they're able to complete more deliveries. Their wages are going to be paid on a per delivery basis. And what these authors do is run a field experiment where they sort of exogenously vary the wages paid to the drivers per delivery. Interestingly, what these authors find is that the bike messengers are actually putting in less effort per shift when wages are increased. Now, this is a little bit odd, right? From a sort of very classical economic standpoint, you might expect that if you're being paid a lot per delivery on Monday and little per delivery on Tuesday, you would work harder on Monday and consume more leisure on Tuesday. But this is exactly the opposite of the findings from this paper. So the authors interpret this behavior and provide additional experimental support, suggesting that the bike messengers are using a heuristic, basically a daily income target. So let's say I want to make $300 today. I'm going to complete just enough deliveries to achieve that $300 income. Now, the idea of having an income target, right, is not necessarily inconsistent with sort of traditional economic models, right? If you say I want to make $1 million before I retire and I don't really need more than that, that's entirely coherent. What's interesting is that this is framed on a daily basis, right? So you're thinking about what money you're making today without considering how much money you'll make tomorrow. So let's try to understand this behavior from a computational perspective. Just to make it a bit concrete, let's think about a worker that on each given day I is choosing whether to put in high effort or low effort. So the effort decision is given by xi. There are n days in total. One kind of behavior that the worker can engage in is to plan one day at a time, like the previous paper suggested. And an algorithm that you could use to plan one day at a time is to simply search over the two actions, high effort or low effort, and do this every day. So do this n times. This algorithm will take an amount of time to make a choice, which is growing linearly in the number of days. And we're going to think about linear time algorithms as being plausible descriptions of the worker's behavior. On the other hand, a sort of, again, more classical economic model might suggest that the agents are planning n days at once. And again, a simple algorithm you could use here, brute force search, is to simply search over all the vectors x, right? Where again, x is going to denote for each day I whether you put in high effort or low effort. Now, of course, there are 2 to the n such vectors, and so this algorithm will take an amount of time that is growing exponentially in the number of days. And as people in this room will be well familiar with, exponential growth is extremely aggressive. And so even if the worker has sort of the computational processing ability of a modern computer, rather quickly as you increase the number of days, the amount of time that it takes this algorithm to make a choice will exceed the lifespan of the worker. So we're going to regard this algorithm as not being a plausible description of the worker's behavior. Now, of course, there might exist other algorithms that take some advantage of the worker's preferences or other aspects of the problem to plan n days at once better, more quickly. So we don't yet want to say that planning n days at once is unreasonable, just that this particular algorithm is not a plausible way to get there. So this little example is going to motivate the research question and the way that I approach that question. So the question is whether behavioral heuristics, like planning one day at a time, are necessary responses to computational constraints. And my approach is going to be thinking about computational constraints as whether there exists a relatively quick algorithm that could have generated those choices. Okay, let me talk about the main definition briefly and then the key results. So the main definition is computational tractability. So choices are computational tractable if there exists an algorithm that generates those choices in at most polynomial time. Right? So we're just adapting a very common definition from time complexity in computer science and applying it to decision theory. My first set of results are going to show that under standard assumptions, behavioral heuristics are indeed necessary responses to computational constraints. More precisely, my first three theorems, I'll only show the first one, will establish that if choices are computationally tractable and satisfy the expected utility axioms, then they are observationally equivalent to forms of choice bracketing. Right? So we began with a pretty general economic model, we imposed computational tractability, and we showed that, in fact, this heuristic that might appear odd is the only kind of behavior that could exist. Okay, now, of course, at this point, we might want to take a step back and ask whether these expected utility axioms, these sort of standard rationality assumptions, are even still appealing in the presence of computational constraints. And that brings me to my final result, which shows that given computational constraints, the standard rationality assumptions are not always normatively appealing. More precisely, for a decision maker who intrinsically cares about the expected value of some objective function, I show that there exist heuristics, or approximation algorithms, that violate the expected utility axioms, but perform better than any tractable choices that are consistent with those axioms. In that sense, the decision maker might be better off if she is willing to engage in behavior that an outside observer like me, looking at her choices, would deem irrational. Okay, so I'm going to pass over related literature just in the interest of time and briefly outline the talk. So I'm going to introduce the model, a decision theoretic model plus the definition of computational tractability. Then I will tell you how tractability relates to choice bracketing. Then I will give you my final result, which revisits the appeal of the rationality axioms, and I will conclude. Okay, so the starting point for the model is an outcome X that belongs to some outcome space script X. This is what the decision maker cares about. Now, I'll define it formally on this slide, but I just want to give you an example of what the outcome is trying to capture before I define it. So think about an outcome X as a consumption bundle, where xi is going to be the quantity consumed of good I. Or think about X as the income from some investment portfolio, where xi is the income earned from asset I. Now, both of these, both the consumption bundle and the investment portfolio, are likely to be very high dimensional. Right? So if you think about going to a grocery store, the grocery store will have thousands, if not tens of thousands or more products. And so the consumption bundle will be on the order of 1,000 or 10,000 or so forth dimensional. Likewise, if you're an investor on the New York Stock Exchange, right, there are almost 3,000 different firms listed on that exchange. And so the portfolio itself will be quite high dimensional. So I want to think about outcomes as these high dimensional objects. And particularly, I want to think about finite dimensional objects that are of arbitrarily high dimension. To do that, I'm going to define the outcome space as consisting of eventually zero sequences. So more precisely, I'm going to think about an outcome X as an infinite sequence of rational numbers, where there exists some number n's, giving the dimension, which such that x1 through xn takes on arbitrary values, but xn plus 1 and onwards is equal to 0. So this vector here is effectively n-dimensional. Okay. Now, as an investor, the outcome you care about is the income earned from the different assets, but you don't really get to choose the income you earn. You get to choose a portfolio, which is linked in some stochastic sense to the income earned. So what the objects that the decision maker is actually choosing are going to be lotteries. Okay? So lotteries, which are just random outcomes, or more formally, are going to map from a sample space, which is 0, 1, to the space of outcomes. You can also think about a lottery as a random vector, right? So again, an outcome, little x, is a vector, and x is a random outcome, so it is a random vector. Each component of that random vector, xi, we're going to call a partial lottery. Notice that the partial lotteries, let's say xi and xj, could be correlated. I also need to introduce the idea of a menu, right? So this is defining the sort of set of feasible lotteries that the decision maker could choose from, right? So this is the decision problem that they are presented with. And script M is a collection of menus, or like the universe of decision problems that the decision maker could be presented with. Finally, we describe the decision maker's choices using a choice correspondence C. This is going to be mapping menus in the collection of menus to lotteries within that menu. Okay, so I'm going to need sort of 2 more slides on decision theory, and then I'll define computational tractability, and then we'll move on to the results. The first thing I need to do is tell you a little bit more about this collection script M of menus. The second thing that I need to do is tell you how I'm going to define rationality. So, of course, I need to make some assumptions about the collection of menus, right? Otherwise, the decision maker might not make any choices at all, and I won't be able to say anything. So a pretty common assumption to make is that the collection of menus includes all binary menus, so all menus with at most 2 lotteries, let's say x and x prime. But for my setting, I also want to think about a decision maker that is making these kinds of high-dimensional choices. So I want to think about sort of like an analog to a binary menu in a high-dimensional setting. Well, the simplest thing that I can think of is a decision maker that makes many binary decisions. So that's what I want to try and formalize. To formalize that, I'm going to introduce the idea of a partial menu. A partial menu Mi is a set of partial lotteries Xi. Again, Xi is just one coordinate of this random vector X. And a product menu is just the Cartesian product of partial menus. Now, the important thing about a product menu is that what I choose in dimension I does not affect what is feasible in dimension J. So the assumption that I'm going to make is that the collection of menus that the decision maker could be presented with includes all product menus with binary partial menus. Right, so that's just the simple analog to a binary menu. Now, of course, the decision maker might make choices from menus that are not product menus with binary partial menus. They might make choices from other kinds of product menus or menus with budget constraints or so forth, and that's all fine. Right? But at the very least, they need to be able to make choices from these simple kinds of menus. Okay, and then briefly define rationality. So I'm going to say that choices C are rational if they can be rationalized by preferences that satisfy the expected utility axioms. Right, so these are the axioms of von Neumann and Morgenstern. If you're not familiar with them, let me give you an equivalent definition. There exists a utility function U mapping outcomes to real numbers such that the decision maker's choices are as if they are maximizing the expected value of that utility function. So this is just one notion of rationality, but it's a pretty commonplace one, and it's an ingredient to many other notions of rationality that we have. Notice that the utility function is just a way of representing the choices. It's an as-if definition, so it doesn't necessarily mean something sort of intrinsic about what the decision maker cares about, and that will be important later on. Okay, and then finally, computational tractability. So I will spend a little bit less time on this than I usually do because this is a computer science heavy audience. But I'm going to say that choices C are computationally tractable if there exists some algorithm A where the algorithm simulates the choices. So it takes in a description of a menu and outputs the choice that the decision maker would have made from that menu. And it runs reasonably quickly, so the amount of steps that it has to take is growing at most polynomially in the dimension n of the menu. Now, one thing to note is that like rationality, tractability is an as-if definition, right? So we're just saying that there exists some algorithm that could have generated the choices, not necessarily that that's the algorithm that the decision maker used. It's also worth sort of being clear, a choice correspondence C, so far I've not said anything about optimization on this slide, right? So tractability just has to do with a single choice correspondence being a computational problem, mapping menus and some collection of menus to choices within those menus. Okay, so now let's move on to the first set of results. So first I want to think about the set of rational choice correspondences, which we defined, and then also the set of tractable choice correspondences, which we also defined. And the goal really is to characterize that intersection, right? So the first thing we might ask is, okay, we have this definition of rationality from economics, this definition of tractability from computer science. When are these two desirable notions compatible? I will give a complete answer to this, at least in the paper, and I'll allude to it later on. But first, I want to sort of start with an easier special case by adding in a third property, which is called symmetry. I'll define it on the next slide. And I'm going to show that rational, tractable, and symmetric choices look like narrow choice bracketing, this heuristic I mentioned at the beginning, or equivalently, like additive separability of the utility function that rationalizes the choices. Okay, so the representation theorem is as follows. So I'm going to say that a utility function U is symmetric if its arguments are interchangeable. In other words, if I replace xi with xj and xj with xi, the utility does not change. This makes sense in some settings, but not in others, right? So in the case of an investor, maybe the investor doesn't care whether they earn money from Apple stock or they earn money from Tesla stock. On the other hand, a consumer probably cares, might view apples and oranges as different entities. So it's an assumption we're going to be using for convenience that applies in some settings but not others, and we'll get rid of it in the more general analysis. I'm going to assume that P is not equal to NP. And my first theorem says that if choices C are rational, tractable, and symmetric, then they can be rationalized by an additively separable utility function. Okay? And additive separability is just defined right here. Now, just to be clear, so we started with basically any symmetric utility function. And we added tractability, and then we got to additively separable utility functions, which is a pretty small subset of all symmetric utility functions. So in that sense, we can use tractability in conjunction with existing economic assumptions that we might view as innocuous to get very strong restrictions and much refined predictions relative to what we would have had otherwise. Now let's try to understand this again in the context of narrow choice bracketing. So to define narrow choice bracketing on product menus M, narrow choice bracketing will optimize over these partial menus Mi separately. In other words, you'll have some utility function Ui specific to coordinate I, and you will choose the partial lottery within the partial menu that maximizes the expected value of that coordinate-specific utility function. Now, again, I just want to stress that this can lead to odd-seeming behaviors. Okay? Things like correlation neglect, things like small stakes risk aversion, but not the more large stakes risk aversion that economists are used to working with, a lack of intertemporal substitution, as we saw in the bike messenger example, and so forth. Right? So a lot of seemingly odd behaviors. But we can observe pretty straightforwardly that on product menus, narrow choice bracketing is observationally equivalent to expected utility maximization with an additively separable utility function. So to reinterpret my theorem 1, we can say that if choices are rational, tractable, and symmetric, each of which seems like a pretty mild innocuous property, then the choices are observationally equivalent to narrow choice bracketing, which leads to all these odd behaviors. Okay, so having given you the special case with symmetry, let me just allude to the more general case, where we want to characterize the set of rational and tractable choice correspondences. What I do in the work is sort of propose a new algorithm called dynamic choice bracketing that combines ideas from choice bracketing and from dynamic programming. And I show that the set of rational and tractable choice correspondences is observationally equivalent to dynamic choice bracketing. I also give a characterization in terms of a separability property of the utility function. So I introduce this idea of Hadwiger separability that basically says there are maybe some complementarities or some substitutabilities across decisions, but their frequency is limited using notions of graph sparsity. Okay, so let me move on, though, in the interest of time, and give you my final result. So I want to think about optimal behavior under computational constraints. So I'm going to think about a decision maker now that cares about the expected value of some objective function U bar. If the objective function is not Hadwiger separable, then exact optimization is not tractable, and this follows from just my previous results. But the decision maker still has to make a choice, and one thing they might do, maybe if they're a computer scientist, is look for approximately optimal choices. So the question I want to ask is whether an outside observer looking at this decision maker's choices would conclude that this decision maker is rational. Or more precisely, whether there exists a utility function U that rationalizes the choices. And what I'm going to show is that the answer is no, at least in some cases. So I'm going to make a slightly stronger computational hardness assumption. And theorem 4 will show that there exists objective functions U bar such that no rational and tractable choices guarantee you any fraction of your optimal payoff for any, for any such fraction. But there exist tractable choices that give you a decent approximation. So in other words, you can get a constant approximation to these objectives, but not if you insist on algorithms that satisfy these standard rationality assumptions. Now, it's natural to ask whether these objective functions U bar are pathological or reasonable. And in this case, I would argue that they're quite reasonable. They include things like maybe an investor who cares about the total income earned across all assets, and then is risk averse with like a typical risk averse utility function. Okay, so let me conclude. So I'm going to conclude using a diagram that depicts what I call the choice trilemma. I find it a helpful way to summarize the results. So we began by introducing these ideas of rationality and tractability and characterizing the intersection. So when are these two ideas compatible? I showed that they're only compatible when you have a decision maker who is dynamically choice bracketing. We introduced this idea of approximate optimality. And of course, tractable and approximately optimal choices are studied in computer science under the heading of approximation algorithms. And finally, we could think about the intersection of rational and approximately optimal choices. This is a little bit less interesting, but it's worth pointing out because it includes something that I think as economists we often have in the back of our minds, which is the decision maker is exactly optimizing her true objective function. If you're exactly optimizing your true objective, then of course your choices will appear rational because you can rationalize them using your objective function, and they will be trivially approximately optimal. My fourth theorem showed that the intersection of these three sets is empty. In other words, while you can guarantee any two of these properties, tractability and rationality, rationality and approximate optimality, tractability and approximate optimality, you cannot guarantee all three. So as a decision maker, if you are computationally constrained in the sense that I've defined, and you need to make, your choice correspondence must be computationally tractable, then you have like a meta choice to make. Either you can be approximately optimal according to your true objective, or you can be rational in the sense that an outside observer looking at your choices would be able to rationalize them. For my part, I would probably care more about being approximately optimal according to my true objective, and so reasonably a decision maker might make choices that are not rational, do not appear rational. Okay, so just to briefly outline next steps, I think there are many ways to apply computationally tractable choice to economics, to get tighter predictions like choice bracketing, useful functional forms like additive separability and other notions of separability that I introduce, to reevaluate existing assumptions like the expected utility axioms, and to obtain simplicity measures on utility functions, which I haven't discussed in this talk. I think there are many interesting theoretical questions as well that I'm happy to talk about offline. Yeah, thank you very much.
Hi, thank you for a nice talk. I was wondering about the role of rationalizability by a utility function versus just ordinal preferences, given that you have a non-countable set of outcomes.
Given that I have non-countable what?
I guess, what is the role played by the requirement that you rationalize by a utility function versus by just ordinal preferences?
I think the idea of having cardinal preferences is common in the setting that I'm looking at because you have uncertainty, right? So if I'm just using the definition of rationality essentially of von Neumann Morgenstern, and that's one that implies cardinal utility. But you could imagine doing this analysis with like a different set of rationality axioms. Maybe that only gives you an ordinal representation. And I can't say immediately how the results would change, but it's an analysis that you could certainly do.
Sorry, I'm a little short. So you just showed exclusivity between three different things: rationality, approximability, and tractability. And I was wondering if you had intuitions on whether the three remain exclusive for the kinds of problems that humans tend to answer, or choices that we tend to have. Because intuitively, the person giving me a choice, or whatever, the system, the society that gives me a choice, is designed by humans, and so they must have had computationally tractable heuristics to give the choices that I'm receiving.
I guess I think there are two ways that you could think about that. One is in terms of for like menus that people typically face. The other one is in terms of like objective functions that they usually have. I would say that pretty clearly, I mean, I didn't go into too much detail, but I think pretty clearly the kinds of objective functions for which the result holds are very natural ones that you would expect to occur in practice. In terms of the kinds of menus, that's an interesting question, right? And I think one direction that would be extremely interesting is, the definition of rationality that I use here, which again is one that economists use all the time, it says that you exactly optimize over all menus in some rich collection of menus, right? But it would be interesting to think about relaxed notions of rationality that only require you to optimize over, a meaningful subset of menus, maybe the menus that people more typically encounter. And I think that's a setting in which you could, ask the question that you're asking and hopefully give an interesting answer. And I think that's a good direction for people to work on. And I hope that's one of the directions people do work on.
Thanks.
Thank you for the question.
Hi, I have a question that is there a more intuitive explanation of whether a choice is tractable or not? Or is there a criteria about what makes a choice tractable while make others not?
Sort of what features of the utility function distinguish tractable from not tractable choices, or why certain features relate to tractability or not?
Yeah.
The latter one?
Yes.
Okay. Yeah, so I think, I mean, if I had a little more time, I'd go through a proof sketch, and I think it would give you a decent intuition. But the quickest intuition I can give, which I don't know how much that'll elucidate, is from the introduction when I talked about the Mike messenger, right? If you're narrowly choice bracketing, you basically solve many low-dimensional problems. If you're broadly choice bracketing, then you have to solve this one big high-dimensional problem, and so you run into recursive dimensionality, right? And so my proof is basically showing that there's no way to circumvent that proof, that recursive dimensionality, without violating, without implying that P is equal to NP. Yeah. Thank you.
Just want to remind virtual people, rather people.
There you go.
So just want to remind the virtual people that they can also ask questions. I guess they can type them, or they can also have a mic there, right?
Yeah, because they stand on the broadcast.
If you stand on the broadcast, they can speak. Okay, but I guess not. They don't have any questions about this talk. So let's thank the speaker again, and then we have a coffee break.